Awesome. Thank you both for that great great presentation about Docker and containers. So I'll be going over Kubernetes basics. We're going to talk about what Kubernetes is, what is K3s. We're going to mention containers, pods, and nodes and how they all relate to Kubernetes. We'll talk a little bit about namespaces, and then we'll go into controllers and their workloads as well. Okay, so what is Kubernetes? Kubernetes is just a really long word for a container orchestration tool. It is one of many options, but it is one of the most popular and the one that we like to use here for Project 3 class, and it's also Greek for helmsman. So that's a fun fact. So why are we using Kubernetes? Like I mentioned, it's very popular, which means there's a lot of documentation for it, so it can be fairly easy to pick up if you go through their official docs, and it is very capable. So it's going to be able to accomplish all the needs that we have within Project 3 class. The other thing is that we want to scale. So like we have mentioned before, we don't necessarily have login or anything for Toynet just yet, but we do plan to have it at some point, and we want to be future facing now so that we don't have to try and implement backwards compatibility in the future. Okay, and then we will also not be using K8s. We'll be using something called K3s. It is a fork of sorts from K8s. It is made and managed by the OpenSUSE Foundation as well as Rancher. All right, so in that case, what is K3s? So K3s is a shorter word for Kubernetes. That was a lot of their intention. It cuts not only the word, but the resources required to run the resource in half. So the diagram here kind of demonstrates what a K3s cluster might look like. This actually isn't very different from what a Kubernetes traditional cluster might look like. One of the main things to note is that there is a SQLite server here on the left side on the K3 server. So that SQLite database is just replacing the etc database that Kubernetes normally uses. This is just a lighter weight database that the author decided would be a better fit for the K3's implementation. There are some other things that the author decided to cut out as well that he felt were unnecessary in Kubernetes to bring down some of what he felt was bloat. All right, so containers are essential to Kubernetes as it is a container orchestration tool. As we talked about, we use Docker, and we just had a great presentation on what Docker is and how it works. But essentially, containers have the application within them. It kind of manages the application. It allows you to spin up and spit down your application as you need, as well as different portions of it. So you can have a database that you can work on separately from the front end or the back end without affecting those. The containers within Kubernetes have to exist within a pod. And this will allow Kubernetes to communicate with the container resources, as well as allow the containers to communicate with one another within the cluster for Kubernetes. Okay, so what is a pod? So a pod is the lowest level of communication that Kubernetes API server can actually talk with. So the pod essentially is just a logical resource that hosts multiple containers. It's usually one or more, but you can host your entire application if you have it split between, say, backend, front end, and database within a single pod, and then you could have multiples of that pod to ensure high availability. The pods are usually built using a pod spec. This is typically written in JSON or YAML format within the file. And that pod spec can, again, specify which containers and resources are within each pod, as well as how many copies of those pods we want. And then pods live on nodes. So nodes are just physical resources. They couldn't be virtual resources such as a VM, but it is the actual physical resources, the CPU, the RAM, the kernel that the pod is going to live on. Nodes can be either masters or workers. So the master node is going to have everything that Kubernetes needs as a server and as a service living on that single node. This will be the Kube API server. There's going to be a controller manager. If you're in the cloud, there's a cloud controller that you can use to interact with the load balancer and other cloud resources that may be spun up automatically for you. And there's also a scheduler, which tells the pods to go to specific nodes. Kubernetes has a capability where it rates each node and how healthy they are, and then it deploys pods and resources as needed to those nodes. So if a node is failing or isn't up, or the Kube API server cannot communicate with it, it will actually give up on talking to that node after about 5 minutes and then reallocate those pods to a different node. Okay, so another concept within Kubernetes is namespaces. These are designed after Linux namespaces, if you're familiar with those, but they essentially provide a scope for the resources. Some unique things about these namespaces within Kubernetes is that they have to have unique names. So you can't have namespace one and namespace one. You can have namespace one and namespace two. And then further within those namespaces, you can't have resources of the same name either. So those names also need to be unique. So for our example, we can have pod one and pod two within a single namespace, but not pod one and pod one. Conversely, we couldn't have something like toynet and toynet within the same namespace. That would be too confusing for the Kube API server to be able to interact with. And then further is that the namespaces are generally designed for larger organizations, not typically used for smaller organizations, because the main usage for namespace is typically to split up the workload between different groups or teams. And so this way you can have a development team or a staging namespace or a administrative team all working on the same resources without actually colliding with one another and causing any production failures. Okay, so another thing we'll talk about is controllers. So controllers manage a lot of the Kubernetes cluster, which is just all of the nodes and pods and resources that exist within Kubernetes that it manages. And so controllers watch these different resources, and they also check the desired state that Kubernetes has, and it tries to meet that desired state. So essentially, the Kubernetes controllers will receive a desired state from an administrator or some other user, and it will check the actual cluster to see if the current state matches that desired state. And Kubernetes, using these controllers, are always going to be trying to change things to make sure that the current state matches the desired state. Now, with this, you can do a lot of different things. So there are built-in controllers that are ideal for high availability and high uptime. Those will be some of our replica sets that will say we want multiples of each pod to ensure that if one of them goes down, that our application still stands and we don't have downtime because of that. And then also daemon sets that will help us accomplish some of the same things as far as keeping services up and running or consistent across the entire cluster. This is useful if we have multiple pods utilizing the same database. So in this case, we could have a separate database for our backend for toynet and then have multiple pods referring to it from our actual toynet pod front ends. Okay, and then we can also do some cool things with controllers. So we can have things that implement order, like our replica sets and daemon sets to keep up our application, or we can have things that actually take down our application, such as Chaos Monkey or Datadog's Chaos Controller. If you implement some of these controllers, they will cause pod and node disruptions and take down your resources entirely. And then you'll be reliant on some of the built-in controllers like the replica set to bring them back automatically, or you'd have to go in and disable those controllers yourself.